of baseball.
Gary Sanchez hit his 9th homer to tie Voit for the team lead in home runs. That's 9. Gary is the batter now.
Drilled deep to left field. There it goes. See ya. Another home run for Sanchez. 6-1 Yanks.
That was just a blast from the New York Yankees, Gary Sanchez, and that was hit about a week ago on May 3rd, 2019. So, ask yourselves, we're gonna ask the question: where did the ball land? Pretty much to find the distance without air resistance, we can just use this nice little graphic right here. It's the arc of the ball is traveling up top here, and point A and point B. So it's a start at A and a B. And we're going to need the essential things we're going to need are the horizontal velocity, the launch angle, theta, and we're going to use these to find the range, or the distance traveled. And so the equation for range is v times cosine theta times t, or v is velocity and t is time. And the first thing we're going to do is swap the t for time out. And there's an equation for time, t equals 2v sine theta over g. And so when we plug that in, that'll be r equals v cosine theta times 2v sine theta over g, and when you multiply those together, you get r equals v squared times the quantity 2 sine theta times cosine theta, and this is all over g. This is gravity. And actually, you can combine this quantity together to create sine 2 theta because of it's a double angle formula, and that gives us the final equation for r. It's r equals v squared sine 2 theta divided by g. So next we're just going to plug in our values in for that equation, and the values that we have are from Statcast, which is a very helpful tool. Every single MLB stadium has it, and it keeps track of the two things we're going to need, which are launch angle and exit velocity. So the launch angle of that hit that you saw was 20.1 degrees, and the exit velocity, or the initial velocity, was 52.885 meters per second. So I'm just going to plug these values into the equation. R equals v squared sine 2 theta over g. And after putting those into the calculator, you will get the value for r, and that will be 183.98 meters. And once you convert that to feet, so 1 meter is 3.28 feet. You get a whopping 603 feet. Now, this number is a little ridiculous. It's nowhere near how far you hit it, but this is because we are not taking into account the air resistance. And pretty much it's a much more inflated number. It's bigger than the legendary Mickey Mantle 565-foot blast. It's completely unrealistic. And so, yeah, that's pretty much what we have. The two components that explain the difference in the value we got and the actual value are lift and drag. So the first one I'm going to explain is lift. And lift is caused by the rotation of the baseball. So when the baseball is hit, a home run, you're actually expecting to strike down the ball, causing a backspin. And so once the ball spins backwards, since it's not completely smooth and has laces, it will actually push air downwards and away from the ball. But according to Newton's third law, there is an equal and opposite action-reaction pair. So the air will also push on the ball and it will drive the ball further. And the second concept to add onto this is drag. And drag is pretty much another way to say the air resistance of the ball, or the force of the air resistance against an object, in this case the ball. And the equation for this is D equals P times V squared times A times CD over 2. And the P is the density of the air, the medium that the object is traveling through. V is for velocity, or is pretty much in a certain instance of time. A is the area of the largest cross-section of the object, so where the baseball is the thickest. And the CD is something called the drag coefficient. So the drag coefficient, or CD, is found by running many experiments on an object in usually a wind tunnel. NASA has found the CD of a baseball is 0.3 compared to the 0.5 of most smooth spheres. This is because the baseball has laces. So CD equals 0.3. The density of air, this was at 15 degrees Celsius. That's when Gary Sanchez hit the ball, and that would be 1.225 kilograms per meter squared. Or cubed, sorry. And the velocity is the same as we had earlier, which is 52.885 meters per second. And finally, we have the area, and the area of the cross section for a circle. I guess the circle from the sphere is the classic pi r squared, found in geometry classes. Everybody knows it. And the radius of a baseball on average is 0.0375 meters. So when you plug the radius into that equation, you get an area of 0.0044 meters squared. And next I'm going to plug these numbers into the equation. I'm going to do that off screen just to save some time. And so once you put the numbers into the calculator, you will get the answer of 4.522 newtons. This value actually is rather odd to actually apply to the distance of the ball and the trajectory, because once this affects the ball, it will actually decrease the velocity, and once the velocity decreases, this will become smaller, and it will then in turn affect the ball less and less, and it will become smaller and smaller over time. And it's actually rather hard to apply a trajectory, and it's something I myself am unable to do, and is something a higher level physics scholar will understand. But also, I guess the density of the air could also be affected pretty easily by the humidity and temperature. So lower temperatures and humidity would raise the density of the air and raise drag as well, while higher temperatures and higher humidity lower density and drag. And pretty much the lift and drag applied to the home run cause it to travel only 412 feet, which is 191 feet down from 603 feet we found with a theoretical value with no air resistance. So I just hope that I was able to teach something about finding a distance traveled, range, and pretty much just some basics of the concepts of lift and drag, and how to find drag, the force of drag. Thanks for watching.